I was sitting in a meeting not too long ago of users of our Frontera system, which most of you know, it's been around for a while. And, you know, speaker after speaker, you know, through a morning. And I was struck by, you know, one of the things we've always said about high-performance computing, right, is it's the universal instrument of science, right? You can help some people by, you know, buying a big microscope. You can help some people by putting a telescope in orbit. Everybody gets helped when we do big computing infrastructure in terms of, unless you're trying to also put a telescope in orbit, when we do big computing. But I was struck by the range of scales in the problems that we see doing that. This was sort of a few months back, but so people were talking about simulations with time steps in picoseconds, and I had other people doing gigayears at the cosmology level, which gives you a 10 to the 28th range. And if you look in the less popular parts of Wikipedia, there's 30 octillion picoseconds in a gigayear. So we have a pretty wide range in octillions there. And then the length scales of those simulations actually had a bigger spread from angstroms to megaparsecs. So we had a 10 to the 32nd spread, which means there are 300 nonillion angstroms per megaparsec. Fit that in your 4-bit machine learning. This is going to be the challenge that we have going forward. But nonetheless, it is hard to find problems that exist in the universe that we can't fit somewhere in that 10 to the 32nd range of bounds from the sort of Planck scale to the width of the universe. So it really is just an amazingly versatile and universal tool, and the fact that we work across these scales on the same systems is just incredible. So, but then AI came along, and the last couple of years I was here, we've talked a little bit about its sort of impact on the scientific workflow, and that has continued to evolve rapidly, but that's not really what I want to talk about, more that the fact what has happened to us sort of in the marketplace. So, so obviously AI's captured the public imagination at this point, for better or for worse. This weekend I was thinking about making some t-shirts that said, "Give Skynet a chance," would it be that much worse? But anyway, but our, what's really happened is the amount of scientific impact is arguable, and how deep the impact will continue to be, I think there's a lot of things that have changed. It's still not going to replace most of our core simulation, but it's undoubtedly going to have a huge market impact. Yeah, and I'm going to give some numbers from the various analysts. I have Addison here in the front row taking notes frantically. But we know the hardware infrastructure market for AI, last year I said it was $300 billion a year. This year I think it's $300 billion for the top 4 companies that are spending on that. Microsoft's announced, even with the rumors yesterday that they're pulling back on some leases, they're still on track for an $80 billion spend this year in AI infrastructure, which is, well, we'll get to the scale of that in a slide or two. But, you know, way over optimistic estimates put economic impact at $9 trillion a year by 2030. Impact on maybe 50% of all jobs on the planet. Also probably overly optimistic. But most importantly is with the problem of that angstroms to megaparsecs and the number of bits you need issue, at scale, the technologies being deployed for AI and for HPC are identical. In almost every reasonable way. In some sense, the few differences we have made HPC a lot harder because of the AI capture of the marketplace, and it's driven the costs of our people and our hardware way up. But hey, we can adapt to that. We've done it before. So, so my assertions here are that AI might replace some of our HPC simulation through things like surrogate models. Certainly for doing fast inference on things that we already sort of understand how to do. I think it's likely that that will happen. You know, you see it, you know, amazing things in like hurricane forecasting, but it's essentially because we pre-computed all the hurricane tracks and we're using the surrogate models to interpolate in between them. And computing is definitely faster if you've already done it. So, but how much is debatable? It's definitely not going to be all. I think it will probably be a significant disruptor in the scientific workflow overall. Even if you're not replacing your model, it's an awfully good way to get a summary of 1,000 papers and everything that's happened in a topic that you want to research in 10 minutes. That is an incredible accelerator all by itself. but I think it is unquestionable that it's disrupted the marketplace for what we do in scientific and technical computing. And so that's what I want to talk about. So I've stolen a few slides. So I'd like to say I remembered which market research firm I stole them from, but I don't. So they actually had me send slides in advance for this meeting. And again, if you know me, you know I don't really do that. But the fact is, I submitted this slide deck not this morning. So I didn't write it this morning. So I have to remember what I put in it. And that's an interesting challenge. So as I riff through. But this is a projection. Might have been Hyperion. So Addison says Hyperion's OK. So I'm going to get away with that. But of the server market sort of before and after the AI inflection point. And you can see the worldwide HPC server market was in the $10 or $15 billion range. Now they're talking about $40 billion for that. Obviously, if you include AI, that $80 billion from Microsoft, a fair amount of it is the physical infrastructure, the data center piece, before you buy the servers. But it's certainly, I believe their budget this year for AI infrastructure is higher than the global server market, not just the HPC server market was in 2020. So, and that's just Microsoft. And there are 3 other companies at roughly that level. But it's created this huge inflection point in servers. This is sort of the pre and post AI projection of spend and how much of it is coming from the companies we're used to dealing with versus the new ones. Also stolen from, let's call it Hyperion for sake of argument, where the spending has gone from 30-some billion in 2022. You can see it has doubled in the last 3 years and then is projected to more or less increase another 50% over the next several years. Again, probably a tad optimistic, but the market has been crazy, right? And so things have happened that have never happened before, right? The last year, the cost per bit of storage, at least in Flash, went up about 60%. The last time the cost of storage per bit went up in a year was never, right? 1945 till now, till last year, it dropped every year, right? On sort of our Moore's Law curve. And then last year, flash storage, which is the silicon process, right? Just because of market forces, went up about 60%. I suppose with an audience with a lot of oil and gas, price fluctuation is something you're fairly familiar with. The other thing I found sort of stunning, not only has GPU time increased dramatically in the cloud, we talked about how expensive GPU solutions are in the cloud, just the demand is so high that CPU time went up as well. I was doing a report. I always include sort of a rough estimate of market value in our UT system reports on things like Frontera, right, which is now a 6-year-old machine, Intel Cascade Lakes. Traditionally, the value of those cycles goes down every year, and then I was just doing the math. I looked up the public rates for the number of server hours we delivered, and it went up 80 million last year to this year, and we didn't do anything different. But it turns out the cloud price increased really dramatically on that stuff. So if you were doing sort of a fixed workload in the cloud, even if you're doing the exact same thing and you're not doing AI, the demand of AI customers drove your costs up 50 or 60% last year. So that's a pretty dramatic impact. Depending on, and again, if you're buying on-prem, you have the same problem in that GPUs again, had the last sort of allocation cycle annually for Frontera was yesterday. And I was thinking back on how we price the CPU nodes versus the GPU nodes. And we did use sort of workstation class GPUs back then. But in 2019, I built those 4 GPU servers with Quadro cards. I think the boxes cost $12,000 all in per box for a 4 GPU server. Today, that's $150 for a modern 4 GPU server in Hopper or Blackwell. But yeah, quad Blackwell server, you're easily $150, of which in that spend, the share that went to the system vendor versus NVIDIA was sort of $3,000 or $4,000. And in the modern $150,000, the share that goes to the system vendor is $3,000 or $4,000, and the rest goes to NVIDIA. Which is sort of an interesting thing, but it has had a lot of side effects. But at the same time, I want to stress that the only reason we have modern AI in the form that it's in, at least, and again, there's many branches of AI, but talking specifically about neural nets and deep learning methods and the sort of generative AI craze at the moment and related techniques, There's actually not a whole lot of new algorithmically in that. I mean, there's a million tweaks on it and a billion papers that have come out in the last few years. But everything about neural nets, whether or not they're recurrent, whether they're feed forward, right? Roughly the scale it was going to take to make it work. Most of those methods were around in the 80s. I built my first neural net and trained it in, I think, 1989 with an Apollo workstation that ran, for days to do 3 layers with 8 neurons. Some of the theory around the neural net stuff goes back to the 50s and 60s, but we just didn't have the computers to do it, right? So we needed faster hardware, but we also needed better algorithms, right? So things have happened on the physics side, improving the silicon process. Things have happened on the architecture side, GPUs being the obvious example. And then tons of things have happened on the algorithm side, right? With BLAS and FFTs and things like that. Still linear algebra at the core for most of these methods, just really small matrix multiplies. And all of that sort of had to hit maturity. And in fact, the thing that really vaunted it forward, and I've mentioned this here before, was the transformer paper, right? The attention is all you need paper, Google 2018. I'm sure you've heard about this by now. But it basically said, in this complicated workflow with many data dependencies, this is the only step that really matters, and it doesn't have data dependencies at the same level as the other steps. So suddenly things that were on a workstation, you could scale across 1,000 servers or several thousand GPUs, and that caused things to just jump forward, as figuring out parallelism often does. And again, it's made our architectures virtually indistinguishable. And again, most of the things we did in the HPC space were sort of necessary to enable this large-scale deep learning, right? Fast interconnects, right? InfiniBand was designed as a storage network, but it only really exists because of HPC, right? Nobody was building it for generative AI in 1999 when the InfiniBand standard was coming together, right? So and if you look at sort of cloud deployments, say 2010 to 2015, they constantly said, why do you invest all that money in fast interconnects? And now they're the dominant consumers of fast interconnects by far. Again, 2023, Microsoft put in 40,000 kilometers of InfiniBand. I have 300 kilometers of InfiniBand in our data center, and obviously this year it's going to be much higher than that. But yeah, so they've become dominant in low latency Ethernet, InfiniBand, Slingshot, all of our interconnect technologies, all built for HPC. Message passing obviously came out of the parallel computing community. The MPI standard, open source, mostly academic and national labs, mid-90s, that we build everything on. It's under the covers in DeepSpeed and the OpenAI models and everything else. They need heterogeneity, right? And the HPC community is where heterogeneity came from. In fact, the original use of GPUs to do something other than graphics, remember the G stands for graphics, in GPU. And then we decided they were general purpose, special purpose processors. But GPUs for general computing was about doing scientific computing, right? When Ian Buck started on CUDA way back in 2003, and for a while we called them GPUs. And then we just gave up because that's a lot of letters and went back to GPU. So we still believe in the 2 bytes of storage thing, like the year 2000 problem. And then they lived on gaming and then crypto, and then the AI codes were built for them natively, and it took off. But the notion of having a heterogeneous hardware system is now essential for AI, but came from HPC. They need fast, large-scale file systems, and they've increasingly discovered that so every good file system is an object store now. So when I say not object stores, I mean not the sort of traditional cloud model of you store stuff in an offline object store and then you instantiate a file system, you copy everything in at the start of your run. You run against that file system and you kill it if you're doing a multi-thousand GPU run, and then you migrate back to the object store at the end. We need the sort of POSIX abstractions on top of the object stores, both from the traditional sort of Lustre set of vendors and now VAST, Weka, all this next generation file systems are about the fact that we still need shared data. We need consistency in the way things are written. We have even worse I/O patterns. We used to be able to pretend that good HPC was sort of large sequential reads and writes, even though it was in fact small random ones most of the time. With AI, it is in fact small random ones, and we can't pretend it's anything else. So as you're doing graph traversal and things like that. You do a lot of 4K I/O, so you just do terabytes per second of it. They need liquid cooling, right? We're building out a liquid-cooled data center at the moment. We've had liquid cooling in our data center back to 2015. And when I was talking to vendors about building out the new data center, every data center company I talked to in 2019, 2020 said, we're going to be air-cooled forever. We can do everything with air cooling, warm air, forced chimneys. We have all these great technologies. We'll do a special one-off water cooling for you guys, but that's just crazy because you guys don't know what you're doing. And then by 2022, they're like, hey, remember those water cooling designs we talked about? We'd like to build that in every single data center we own. And if you look now, they're all being refit, underfloor cooling, fast liquid. Our Blackwell racks we're projecting at 225 kilowatts per cabinet for this year delivery. So it's no longer a long future thing, it's a right now thing. I mean, if your definition of rack is the sort of standard size, there is no air cooling solution that's ever going to work for that, right? If your definition of rack is 2 acres, I can probably handle getting enough airflow through that. But if you're, say, I don't know, perhaps we're going to cool some Blackwell chips with it. And the module's this big and it's 2,700 watts, which is what they are. You're going to have a lot of fun trying to cool that with anything other than pumping liquid through it really fast, or boiling liquid off it and recondensing it, which we have at least one vendor doing in our data center right now in an experimental case. So we have negative pressure, two-phase liquid, immersion, all sorts of things going on with a whole bunch of vendors we're working with. So all of these are sort of HPC innovations that the AI community has just sort of stolen and subsumed. And then they decided you should just take all this brilliant stuff and then add Python to it and everything will be fine. And that's sort of my next point here is that a long-time HPC lesson, which I can't spell apparently, lack of use of AI, is that as your scale grows, you need to pay an additional amount of attention to both algorithms and code efficiency, right? Particularly your core code. And somebody asked at the first talk, right? How much does your lines of code change? It's changed dramatically and negatively, but the amount of lines that matter, I don't think have changed that much. I was installing I think Falcon, one of the LLM packages on my laptop, Mac, a few months back. And to just do that, if you start from sort of homebrew and then you add, it's 2,500 packages to get PyTorch running, Python running, PyTorch running, all the associated stuff, the large language model, and the stuff that builds on top of it. There's tens of millions of lines of code there. Most of them execute once, so I don't really care, right? So it's the ones that execute in the inner loops that really matter for performance. But if you don't pay attention to algorithms and code efficiency, you're going to be in trouble. And I said some about this last year. I've been saying to all sorts of people that, yeah, the infrastructure spend is great, but the push in AI has been, how can we get the biggest model out and claim that we have it the fastest, right? And cost be damned, and energy be damned for that matter, right? Doesn't matter how much power it takes. The only factor that has mattered is how soon can I get it? And I hear some hysterical pricing stories, what some of these places are paying, maybe 30x what we typically pay for stuff, because they want it right now. But if you pay attention to code efficiency, you can do a lot better. And I've been sort of screaming into the wind about this, and nobody listened. And then DeepSeek came out, and that got about $589 billion of attention that day in terms of the NVIDIA price drop related to that, which also tells me that the stock market isn't as deep and insightful as I might have thought. But based on a quick analysis of what we've seen from DeepSeek, I have another slide on this. Right, there's nothing truly revolutionary there. It's real attention to best practices and efficiency and using the hardware effectively and writing good code. Okay, it's probably not good code, but code that's not as bad as other code. So people are like, what's your definition of good software? I'm like, I assume I'll know it when I see it, but I haven't yet. So so part of this drive to greater infrastructure, and I'm watching the clock, is that I might have shown this one before, is that we are losing the connection because of it's not a good AI model unless you spent $10 billion to train it. The sort of the basic connection between academia and research teams versus what's gone on in industry. And so this chart just goes back to 2005, and for some publications, it's an Our World in Data chart, a definition of what is a significant AI model. It tracks the number that came from academia, and over time, having it start in academia and then migrate to industry is the right trend, but we've gone from 2005, 6, 7, it being 100% academia to it being like 10% academia by 2023. The green line there is industry, and then there's a lot of industry/academia, which means I needed all the GPUs at Microsoft or Amazon to run the research. So, but you see that academic slice is getting fairly small, and other, meaning foreign government, is getting interesting too. So, and I've already alluded to all this, but with all the great things that happen in AI, there are some drawbacks, right? Again, to work from angstroms to parsecs, you need precision, right? And to figure out, does this connection between this neuron and this connection between this neuron, is it particularly important? That doesn't need a lot of resolution, right? In fact, the neuroscience says your brain runs 22 to 24 levels that you can distinguish between and when a neuron fires as to how strong it is, so that you need 4.5 bits to do that effectively. But we've always done work at 64 bits, and AI has been 32, 16, 8, now 6 is the headline numbers for Blackwell. And we're getting no progress in 64-bit circuits, essentially. And if you look at all the vendor roadmaps, we're not going to get any progress anytime soon in 64-bit performance. And we're not used to living in a world where 64-bit performance is flat and the chips cost twice as much every generation. So that's the opposite of what we've been looking for. Maybe that means at some point we need to pay attention. And as I've said, the AI race has thrown off any thought of cost, efficiency, carbon, any of that stuff in the overarching quest for performance. So Microsoft, who assumes that no one follows history, which is probably a fairly safe bet, is restarting 3 Mile Island, right, to run an AI data center. Lots of interesting 3 Mile Island stories from the 70s. But there's really the entire sort of small modular reactor nuclear power industry is driven by AI data centers at this point, right? Multi-gigawatt things. I actually gave a talk in New Zealand last week. If you take the public numbers for AI data centers that are under construction right now, it's 75 gigawatts. That's 657 terawatt hours a year. I figured that I was in New Zealand last week. It's 17 New Zealand years of power, right? 17 times the size of New Zealand to run AI data centers, because they use 39 terawatt hours to run the country last year. New Zealand, roughly the size of Japan, 100 million less people. But if there's my message to take forward out of this, and then I have a bunch more stuff we won't get to, but you all know I brought 70 slides or something, right? But I think we need 2 big R&D pushes at the moment to move this forward, which we'll do with no government budgets in the future. So one is a focus on how we do essentially what DeepSeek did and raise the efficiency of the AI computation we're doing, because we're computing an awful lot of zeros that we already know are zeros in these interneuron connections, right? They're giant sparse matrices. We don't use any sparse matrix methods. We're using gradient descent to figure out convergence. Good 1860s numerics there. Sort of nothing in advanced numerical methods has made it over to a lot of the AI space. And so whether you're trying to save the world from climate change or save the world from bankruptcy at the rate we're spending on this, I think we need to focus on AI efficiency. And then for the rest of technical computing, what we do, what all of us did before AI took away the last seats in the room at this conference was, and every other conference, is figure out how we're going to exploit this AI hardware in the scientific context, right? Which is going to mean some mixed precision and a whole bunch of things. But and the good news is there's a ton of evidence, even beyond DeepSeek, that this is going to work, right? So part of it is a huge amount when we talk about large-scale system efficiency has been lumped into the data center efficiency conversation, right? What can I do with water cooling? What can I do? Water versus air cooling. Can I schedule better to improve my thermal distribution and raise power? This was an important discussion to have, especially 10 years ago when a lot of data centers were at PUE of 2 or 1.7. But now all good modern data centers are at like 1.2 or 1.1. So we're suffering your standard Amdahl's law problem here, but diminishing returns, right? There's only, between us and perfect data centers is about 10% of the power, and getting to perfect is really hard. Between us and perfect software, 2 orders of magnitude maybe, right? 1,000%, 10,000%, somewhere in that range that we can get. And I'd rather focus on that, right? So we know, for instance, when we move to GPUs, peak flops go up 5 to 6x per watt, right? And it's just a circuit organization. Really, it's about pushing work to the programmer. But anytime I can get a 5x improvements in performance per watt, that's a lot better than trying to squeeze another 10% out of my data center, right? It's just, whole numbers are better than single-digit percentages. So code efficiency gives us a lot of ability. And again, doing a crappy job on software when you can get a 10x, like the DeepSeek guys just did, is better than doing a great job on your data center where you're going to get 10%, right? So if I can get, if I'm get a fifth of what's available in software, I'm going to get a 2x multiplier. So this is sort of the GPU-CPU power ratio. You've seen that. The gist of this one is simpler circuits, pushing the work back to the programmer, increases your lines of code for things like CUDA, but it reduces your power footprint, and that's why GPUs work in the first place. And there's a ton of other places we could exploit that. Again, DeepSeek, if you really look at what they did, mixture of experts, really deep mixture of experts. They used 256-way expert composition. Most people are using 8 or 16 or just doing one big model. If you're doing one big model, well, it turns out it's, again, the parallel computing lesson. Somebody looked at the expert models and how they work for LLMs and said, what if we built a Beowulf cluster of this stuff? The standard Slashdot joke going back 30 years in Unix of, for any technology, what if we just built a cluster of those? And that's essentially what they did with mixture of experts model. And so instead of having one big model, they have 256 little ones. Sounds a lot like the parallel processing argument, right? They did really good data curation. They figured out what to run on the CPU versus the GPU. They did do some stuff to advance the model, but 99% of what they did was taking best practice to the extreme and writing efficient code. So we can do this, and we should, right? This is just sparse versus dense algorithms and how much, that's a factor of 6 on a Cholesky factorization. There's so many things that we can do, right? Memory bandwidth got mentioned. We've benchmarked, we can see like 70% improvements in performance with higher memory bandwidth on chips at the same level of watts, right? Just, it's an organization thing. If you can remove the memory bandwidth and the architecture, same power per socket, same peak watts, flops, your codes go faster. And there's a ton of those type of optimizations out there. You can run on the right number of cores for maximum power efficiency. That is not sophisticated numerics. This is from a paper about sort of carbon versus cores, and almost every speed-up curve looks like this, right, where you have a knee at the bottom and then it sort of flattens out, but you run on the rest of the cores because they're there. But if you ran 2 jobs on that socket at half the cores, you'd get twice the efficiency out of what you did. So there's hard things, reduced rank algorithms, figuring out how to use sparse algorithms, pulling out higher order methods, or you can just pick the right number of cores, right? And that's not that hard. So we've actually seen this in a ton of our benchmarking. Let me just wrap up by saying, as lunch is here, that we've done a lot this year looking at switching to ARM, and we're going to do that for our next major system. And part of the argument, so we deployed a Grace Hopper system this year in Grace. This is sort of raw performance where NVIDIA's blue and Intel's green, in case anybody ever accuses me of being a marketing shell. And this is actually comparing Sapphire Rapids HBM to Grace, the 72-core ARMs from NVIDIA on a dual socket system, and an older AMD, so it's unfair to AMD here, but because it's a Milan, it's just what I had. And one, by the way, in the speed-up curve is Frontera, an Intel Cascade Lake, a sort of 2019 state-of-the-art chip, and sort of code performance. And you see that our fastest single socket at the moment, for most codes, but not all, is the Intel Sapphire Rapids with HBM. The problem is that dual socket server runs at 1150 watts. The Grace one runs at 500 watts. So if I divide by power, it looks like this, and normalize per kilowatt, and suddenly the ARM despite the relatively immature software chain, is again, nothing is universally better in the world of software because there's such a range of algorithms. But for major codes, 8 out of 9, it becomes our best performer when you factor in watts. So again, we can do this stuff. So we have actually started on building the leadership class computing facility. Everybody who knew anything about the finances of it at NSF resigned 2 hours ago this morning, and their last day is Friday. So that should be great on our billion-dollar project. I'm sure bringing new people up to speed that the government's not allowed to hire will work awesome. But we have built our new data center. That's the outside. We're working with Saby Data Centers on it. The inside needs a little work. It's not quite ready for 250 kilowatt racks, but we will be by October. And we have big machines coming, which I've talked to you about before, and we've sort of stuck with that plan for Horizon. So with that, let me stop. Quick plug for Addison, by the way, with all the stuff that's changing. One place to talk about it is Halo, where we have these conversations about, isn't your spend on AI kind of crazy right now? And wouldn't it be nice if you bought $10 billion of GPUs to know what a scheduler is? It's free. You have to put up with Addison, but otherwise it's free. But if you want a chance to share thoughts, it's free, and we can discuss stuff like that. So let me stop. I've gone way too long. So appreciate your time once again, and questions and lunch.
Addison gets his first shot.
Oh,
Thanks,
sure.
Steve.
You criticize
Thanks,
one
Dan.
guy on a slide, and you give him the mic first. Yeah.
Thank you for the talk. That was excellent. My favorite thing out of all of them, and there are a lot of favorites, was when you talked about the need to adapt HPC to what's going to come out on the AI side. As an example, I heard it posited, well, no problem, you can emulate FP64 with int 8, right? That's a possibility, I guess. When you say we're going to have to adapt,
do that. Yeah.
when you say we're going to have to adapt, how do you envision that? What kind of projects will TAC be going forward with to say we've got to start adapting HPC to what we can get on the AI side?
Yeah, so there's a ton of things we can do that are going to be, again, I think this needs to be a large research program, bigger than any one center. But for instance,
we'll get government funding for that.
Where can we use mixed precision, right? Can we build Jack Dangara's looked at mixed precision libraries where you start in 64-bit and end in 64-bit, and you do all your inner iterations at 32-bit, and you can get the same quality of answer, right? So those kind of algorithmic changes have enormous potential, right? There are places where we can actually use AI to do parts of it, right? Plug in surrogates. We should figure out where that is. There are places where we can use lower precision and then use the old there's a library that's been floating around for 2 decades, right, that does unlimited precision, right? If you want to do 128-bit or 256-bit, it does it by chaining smaller floating point operations together. It's way more expensive, maybe 8 or 9 times more, but if 16-bit, as it currently is 60 times faster than double precision, and I use an 8 times less efficient algorithm but have 60 times the raw performance, I win, right, by a factor of more than 6. And if I can get a factor of 6 out of that, awesome. So, so I think, and then again, there's reformulations to look at to make your algorithms actually less sensitive to precision moving forward. So there's a huge range of things to do. We'll probably start at just trying different precisions and then figuring what we can get away with between single and double, probably not. And in particular, for matrix algorithm, can you get to the TF32 instead of FP32? Because that's a 7-to-1 boost right now. So, there's a wide range. I look at it like the transition we made in the late 80s and 90s in HPC from big silicon vector processors to buying commodity microprocessors, right? And we just had to figure it out. And there was a huge argument. The famous Danny Hillis, Seymour Cray argument in HPC was when Danny Hillis was arguing for widespread parallelism, and Seymour Cray said, yeah, if you have to pull a plow, do you want 2 oxen or 1,000 chickens, right, to pull that? But it turned out the answer was 1,000 chickens. It's counterintuitive, right? But that's what every cloud cluster system, Cray, whatever you buy is a multi-thousand node system at this point because with enough algorithmic cleverness and decades of beating on it, we got it to where it wasn't 10% of the algorithms that were friendly to clusters, it was like 80% that were. And we just have to do the same thing. 1,000 chickens, that's your takeaway. Yeah.
One last question. Well, Dan, thank you very, very much.